Problem 3 is about integration. We have a couple of integrals here which we can solve using the techniques we've seen in the lecture. The first integral is over e to the x divided by 1 plus e to the 2x. Well, if we don't have a better idea, let's try to simplify this. This is e to the x divided by 1 plus e to the x squared dx, and let's substitute. We can substitute e to the x, then du is equal to e to the x dx, so this is the same as the integral over 1 plus u squared du. As antiderivative we get the inverse tangent of u plus c, and that gives us, back substituting, the inverse tangent of e to the x plus c. And that's the solution. In part B, we have the integral over a non-standard exponential function. Again, if we don't have a better idea, we write it in terms of the standard exponential function. This is e to the x times logarithm of 2, right? We apply e of logarithm of 2 to the x and then use the logarithm rules. Logarithm of 2 to the x is x times logarithm 2. Okay, and now we have an exponential function there, just not e to the x, but e to the x times logarithm 2, logarithm 2 being a constant. So what we get as antiderivative is 1 over this constant times e to the x times logarithm 2 plus c, and that finally is 1 over the logarithm of 2, again bringing this in the form as 2 to the x times 2 to the x plus c. Part C is about integrating the quotient sine over cosine. What we are doing here, and this is a problem which you might even remember having seen in class, because this is the tangent function, we do a substitution. We substitute the cosine. So we get that du is equal to minus sine of x. We have a sine of x in the numerator which fits in perfectly. So this is minus the integral over 1 over u du, which is minus the natural logarithm of the absolute value of u plus c, which, substituting back, is minus the logarithm of the absolute value of cosine of x plus c. Part D is a problem for inverse trigonometric functions and completing the square, but we have already helped you here. We have done the hard work of completing the square. So we have brought it into a form where we have x plus or minus some constant square, and we have some absolute term here. Okay, so now the first thing to do is to substitute the x plus 1. U is equal to x plus 1. Du is the same as dx, and we get the integral over 6 divided by the square root of 4 minus u square du. Next we want to get rid of this 4. We would like to make it a 1. How can we make it a 1? By being able to pull a 4 out, and then we need to pull a factor 4 out of this u square. So we want that u square comes with a factor u. So what we do is we want to substitute that u is equal to 2 times v, because then u square is equal to 4v, which means that v is equal to 1/2 u and dv is equal to 1/2 du. Doing this substitution, what do we get? We get 1/2 dividing by 1/2 gives us a factor 2. So we get 12 in the numerator divided by the square root of 4 minus 4v square, 4v square being 2u in parentheses square. We can now take this common factor 4 out, take the square root, this gives us a factor 2. The 2 cancels with the 12, which again becomes a 6. So we now have 6 as a factor. Now we have 1 over the square root of 1 minus v squared. This is the inverse sine of v plus c. Substituting back gives us 6 times the inverse sine. V was 1/2 u and u was x plus 1, so 1/2 x plus 1 plus c.